Welcome, ladies and gentlemen, to Chapter 2 of my course on linear algebra in 2D. In this video we are going to learn about the essential geometric transformations of the plane. So first we're going to learn what linear transformations are, also known as linear maps. And then I'm going to go through the major examples, so rotations, reflections, shearings, scalings, and projections. Then also look at some nonlinear transformations, such as translations and more general affine transformations. And finally, we're going to see how we can represent all of these linear and non-linear affine transformations in a unified way. First, we're introducing linear transformations. Now we've seen already that addition of vectors and multiplication of vectors by scalars can be immediately interpreted in a geometric way in Chapter 1 of this course. And there are also other types of geometric transformations that can act on vectors, for example, rotations, reflections, shearings, scalings, and translations, and we want to get to know these better in this video. But first, we have some general considerations. So, by capital phi, Greek letter phi, I denote a geometric transformation, and the key property that such a geometric transformation can have is linearity. What linearity means is that for any two vectors, x and y, and for any scalar lambda, we have the following two laws. Phi of lambda times x is the same as lambda of phi applied to x, and also phi of x plus y is the same as phi of x plus phi of y. So in a sense, a linear map phi or a linear transformation phi is compatible with the algebra of vectors. Now, linear transformations are the central objects of interest in linear algebra, and except for the translations, all of the aforementioned types of transformations are in fact linear. Let's study linearity a bit further. So, recall from Chapter 1 of this course that any vector x is a linear combination of the canonical basis vectors e1 and e2. So if we use this when looking at a linear transformation, it has the following property. Phi applied to the vector x is phi applied to this linear combination x1 times e1 plus x2 times e2. So recall that x1 and x2 are the two components of the vector x. And we can write x as this linear combination, scalar x1 times the first canonical basis vector plus scalar x2 times the second canonical basis vector. And now we apply the linearity property of phi. First, this is the same as phi of x1 times e1 plus phi of x2 times e2, and now we can move the factors x1 and x2 out of phi in each case here. So this becomes x1 times phi of e1 plus x2 times phi of e2. And this is a very important formula here, so we give this a number, formula number 1. And we find the following, proposition 1. The linear map phi is already completely determined by the values of phi of e1 and phi of e2. So this means when we know these two values here, the value of phi on just these two canonical basis vectors, then we know everything we have to know about phi. We don't need any additional information to compute phi on any given vector x that we give it as input. Let's prove this. So suppose there's another linear map, let's call it psi, which takes the same values on the canonical basis vector. So psi of e1 equals phi of e1 and psi of e2 equals phi of e2. And what I want to show is that psi is identical to phi. How do I do this? I take any input vector x and look at the value psi of x, and I want to show that it is equal to phi of x for arbitrary input vectors x. Now, x I can write again as this linear combination, x1 times e1 plus x2 times e2. And now I use the fact that psi is also a linear map, so just like I did up here for phi, I can take apart the sum first, psi of x1 times e1 plus psi of x2 times e2, and then I can take out the scalars. So this is equal to x1 times psi of e1 plus x2 times psi of e2. And now I can use this. I can use that psi and phi have identical values on the canonical basis vectors. So I can replace these two here by phi of e1 and phi of e2. So I have this expression here. But this, as we saw in equation 1, is just phi of x. So what I've shown is that for any input vector x, psi of x equals phi of x if they coincide on these two canonical basis vectors e1 and e2. So phi and psi coincide on every x, hence these two maps are identical. And this is what I mean when I say phi is already completely determined by its values on the canonical basis vectors. Now, as a little exercise for you, pause the video for a moment and show that every linear map maps the null vector to itself. So phi of 0 equals 0 if phi is a linear map. And the solution is as follows. For any vector x, we have by linearity the following. Phi of 0, we can write this in a complicated way by writing the 0 vector, the null vector, as x minus x. So this is the null vector. But then I use linearity to write phi of x minus x as phi of x minus phi of x. But this is again the null vector. So I have some vector here and some vector here, which is the same. And I subtract them and I get the null vector. So phi, a linear map phi maps 0 to 0 again. And a very helpful tool in the study of linear transformations are matrices. So let's see how they come into play here. We have our linear transformation phi, and as we just learned, the only values we need to completely determine phi are its values on the standard basis vectors e1 and e2. So let's say phi of e1 is the vector with entries a1, a2, and phi of e2 is the vector with entries a3 and a4. Then, as we just saw, phi of x is equal to x1 times vector a1, a2 plus x2 times vector a3, a4. Because these two are just the values of phi on the canonical basis vectors. And if we write this out into one vector, we get the vector which has in the first row the entries x1 times a1 plus x2 times a3, and in the second row x1, a2 plus x2 times a4. And now an efficient representation of the transformation phi is given by this matrix here, which is a 2 by 2 matrix to be precise, so it has 2 rows and 2 columns. And what we do, we take the 2 vectors here to which our canonical basis vectors are mapped, and we write them behind one another as the rows into this matrix. So this first, as the columns into this matrix, this first column is the image of e1 under phi, and this second column here is the image of e2 under phi. And as we just saw in proposition 1, this matrix A contains all the information required for the transformation phi, because these 2 vectors here are all we need to completely determine the linear map phi. And we can define a multiplication of matrices and vectors by the following rule. If our matrix A is given with entries A1, A2, A3, A4, and the vector x is given with entries x1, x2, then the product of matrix A by vector x is basically what we just saw on the previous slide, A1 times x1 plus A3 x2 and A2 x1 plus A4 x2. So let the colors help you a little bit to unconfuse this expression here. What we do is basically we take the rows of the matrix, and for each row we multiply it with the column of the vector. Okay, so the first entry in one row is multiplied with the first entry in the column of the vector, and the second entry in the row is multiplied with the second entry in the vector column. And if A was the matrix that we established for the linear map phi, then this matrix vector product is precisely what we get when we apply the linear map phi to the vector x. So this matrix vector multiplication does in fact represent the application of linear maps. Now in particular, we have that if we multiply the matrix A by the first canonical basis vector, we get the first column of A, this one. And if we multiply A by the second canonical basis vector, then we get the second column of A, this one here. And phi is a linear map, and this linearity of phi here appears as the distributivity of matrix vector multiplication. So that means A times lambda vector x is the same as lambda times A times vector x. And A multiplied by vector x plus y is the same as A times x plus A times y. So you see the linearity of phi directly translates into these two properties for matrix vector multiplication. And conversely, if we are given any matrix A with entries A11, A12, A21, A22, then we can use this to define a linear transformation simply by defining phi index A applied to x as the product of matrix A times vector x. And for this we use the rule we just learned on the previous slide. So we have a one-to-one correspondence between matrices and linear maps. So every linear map defines a matrix, and every matrix defines a linear map. Now, you might ask, why do we have these two concepts then to begin with, linear maps and matrices? So why don't we just consider matrices or just consider linear maps? Well, as we will see later, coordinate systems are not always given by the E1 and E2 axis. So we don't always use our canonical basis vectors to describe coordinates. And the matrix for a given linear map is dependent on the choice of the coordinate system. So matrices are very convenient to compute stuff, but they depend on a choice of coordinate system. Whereas if we just look at abstractly defined linear maps, they're usually independent of coordinates. So sometimes for theoretical arguments, it's easier to use linear maps. Whereas if you want to do concrete computation in a coordinate system, then matrices are the method of choice. And we can not only multiply matrices by vectors, but we can also multiply different matrices with one another. So let's say we have two matrices, A and B. And then the rule for multiplying matrices is the following. A times B is matrix A here, multiplied by matrix B here. And yeah, I'm not going to read out the full formula, but what we essentially do is we apply matrix vector multiplication to each column of B individually. So we just learned how we multiply A with the vector x, and now what we do, we take matrix A and we multiply it with the vector that's given by the first column of B. Then we get the first column of A times B, and Then we multiply A by the second column of B, so by this vector here. And this gives us the second column of the matrix product A times B. It's important to note that matrix computation is not commutative. So in general, if you have two matrices A and B, you will not have that A times B is the same as B times A. Sometimes this can happen in very special cases, but in general, they are not the same. So you have to be careful there when reasoning about matrix multiplication. And for this, I have a little exercise for you. So you have two matrices here. So the one matrix A with entries 2, 0, 0, minus 2, and the matrix B with entries 1, 1, minus 1, 1. And now pause the video for a moment and compute the two matrix products A times B and B times A and compare them. And if you've done this, and I hope you did it correctly using the formula from the previous slide, we get the following. So yeah, you can, if you want to verify it, pause the video and check the computations here. Not going to read it all out, but A times B turns out to be the matrix with entries 2, minus 2, minus 2, minus 2, whereas B times A turns out to be the matrix with entries 2, 2, 2, minus 2. And what we see is that these two matrices are clearly not the same. So here we have an example where A times B is not equal to B times A. And this is what you have to expect in general when multiplying two matrices. Now, what is the geometric meaning of matrix multiplication? So when we multiply two matrices by one another. If we're given matrices A and B, then we have the two linear transformation that are defined by multiplying a vector with A and a vector with B. So how does this relate to the matrix product? So if we apply the matrix product A times B to a vector X, this is the same as multiplying matrix A by the vector we obtain by applying the matrix B to the vector X. And this here is the same as applying the linear map phi index B to the vector X. So overall we have matrix A multiplied by the vector phi index B of X. But multiplying this by A is the same as applying the linear map phi index I to the vector phi index B applied to X. So, and we call this phi AB. So this is the linear map defined by the product of the two matrices AB applied to X. So what we find is that the product of two matrices represents the composition of two linear maps. So matrix product AB is the matrix representing the map phi AB, where phi B is followed by phi A. And the composition phi AB is determined by the matrix A times B. So in particular, what follows immediately from this proposition here is that the composition of two linear maps is also a linear map. Because the composition of two linear maps is a map that is represented by a matrix vector multiplication. Now we're getting acquainted with some particular geometric operations on the plane, and we start with the rotations. The task is rotate any vector x counterclockwise by the angle alpha, which is between minus pi and pi, about the origin. So our center of rotation is the origin of our coordinate system. And this rotation we will denote by phi index alpha. And we want to derive a formula for phi index alpha applied to a vector x now. And what we do, we use a little trick. We represent x in polar coordinates. So if x is our vector with coordinates x1 and x2, so the Cartesian coordinates are x1 and x2, then we can use polar coordinates to describe these. So x is here, and it has distance r from the origin. That's the length, or as we learned in the previous chapter, r would be the norm of x. And now we have an angle beta between x and the first axis here, and the E1 axis. And I want to describe x1 and x2 in terms of this angle beta. And as we know, we have a right angle here. So we have a right angle triangle with hypotenuse length r. And so this means this leg has length r times cosine of beta. And the leg opposed to the angle beta has length r times sine of beta. So this is the x2 coordinate of x, and this is the x1 coordinate of x. So we can write the vector x as r times cosine beta in the first coordinate and r times sine beta in the second coordinate. Now what the rotation by the angle alpha does, it takes the vector x and it rotates it. Before it had the angle beta with the E1 axis, and now it's rotated further by an angle alpha, so it has angle alpha plus beta. And that's easily expressed in this polar coordinate representation, because all we have to do is replace the angle beta we had before by the angle alpha plus beta. So x that we had before is now mapped to phi alpha of x, the rotated version. And this has coordinates r times cosine alpha plus beta and r times sine alpha plus beta. So now we have a representation of the rotated vector phi alpha of x in polar coordinates. And we want to get back to a representation of this rotated vector in the Cartesian coordinates x1 and x2. And what we can do here, we use some trigonometric identities that you may or may not have learned in school for the angle sums. And we use the fact that x1 is r times cosine beta and x2 is r times sine beta. So recall we just had that 2 slides before when we introduced the polar coordinates. And now phi alpha of x is the vector with coordinates r cosine alpha plus beta and r sine alpha plus beta. Applying trigonometric identities here for angle sums, we find that this is r times cosine alpha times cosine beta minus r times sine alpha times sine beta. And the second coordinate is r times sine alpha cosine beta plus r cosine alpha sine beta. And please note the colors here. x1 in blue, x2 in red. So you see the highlighted blue terms here give x1 and the highlighted red terms here give x2. So I can rewrite this as cosine alpha times x1 minus sine alpha times x2 and sine alpha times x1 plus cosine alpha times x2. And now we have the representation in the coordinates x1, x2, depending on the rotation angle alpha. And if we take a close look at this and recall the formula for matrix vector multiplication, we note that we can in fact express our rotation as follows. So phi alpha of x is the matrix here with entries cosine alpha, sine alpha, minus sine alpha, and cosine alpha multiplied by the vector x with entries x1 and x2. So the rotation can be expressed by a matrix vector multiplication, hence it is a linear transformation. And it is determined by this rotation matrix here, which we will usually denote as R index alpha. So this is something you should memorize. This is a very important matrix that appears quite frequently in geometry. Now if we compose two rotations, say phi beta and phi alpha, then of course this will yield the rotation by the sum of the two angles. That's geometrically clear. And we can calculate that algebraically. So phi alpha applied to phi beta of x is rotation matrix alpha times rotation matrix beta times x. Here I write out these two rotation matrices explicitly times vector x. Now it's a bit of work multiplying these two matrices by the rules for matrix-matrix multiplications. Yeah, we get these big messy terms here, and applying some trigonometric identities again, we find that this is cosine alpha plus beta, sine alpha plus beta minus sine alpha plus beta, cosine alpha plus beta multiplied by x. And this is precisely the rotation matrix for the rotation by alpha plus beta. So indeed, this algebraic computation proves what you would expect geometrically anyway, that if you rotate by alpha and then by beta, you get the rotation by the angle alpha plus beta. Now observe that alpha plus beta is of course the same as beta plus alpha, so it doesn't matter whether we first rotate by the angle beta and then by alpha, or if we first rotate by the angle alpha and then by beta. So the rotations in the plane are in fact commutative, so they're independent of their order. But be very careful, this is no longer true when you change to 3D space. So in three-dimensional space, composing rotations by different angles is not independent of their order, because you can rotate about different axes, so it can very well depend on the order there. But in two-dimensional space, in the plane that we are looking at the moment, the order of rotations is not relevant. Next up, we look at reflections. So a reflection across a given axis reflects a vector x along the perpendicular line to this axis. And as a simple example, I want to consider a reflection that I denote by the letter sigma. I call it sigma 1 because it's a reflection across the E1 axis. So this is the E1 axis, which is spanned by our first canonical basis vector E1. And reflecting about this axis means if I have a vector x here, then I take its mirror image on the other side of that axis. That means if it has coordinates x1, x2, then I keep the x1 coordinate, but I flip the sign of the x2 coordinate. So the reflection of x1, x2 across this axis here is just the vector x1 minus x2. And it's very easy to represent this particular reflection. For this we have the matrix that I call S1, which just has entries 1, 0 and 0, minus 1. So if you think about it, multiplying this with any vector here, which is on the reflection axis, then it won't change this vector at all. So this is a multiple of the first canonical basis vector E1, and this will just be multiplied by 1, 0. So it will be mapped to itself, whereas any vector lying on the E2 axis will be mapped to its negative, which is reflected by this entry in the matrix here. Maybe compute some examples to fully convince yourself of this. Yeah, we can verify this directly. S1 times the vector x. If we multiply this matrix by the vector with entries x1, x2, we get the vector with entries x1 minus x2. So precisely what our reflection sigma 1 does. And since we can represent sigma 1 by this matrix multiplication, we also have shown that sigma 1 is a linear map. And in a very similar manner, we can determine the reflection across the E2 axis. This is represented by the matrix S2, which has entries minus 1, 0 and 0, 1. But it's not really obvious how we would represent a reflection sigma L across an arbitrary axis L going through the origin. Now, look, if we have this axis L here, and it has some non-trivial angle alpha with both of the coordinate axes, then we would take any vector x here and flip it across this axis here to its reflection, but it's not immediately obvious, as I said, how we would describe this using a matrix, but now we want to derive the matrix representation for that, and we use a little trick. We will reduce sigma L, the reflection across this axis here, to the easily computed reflection across the E1 axis. So we will somehow reduce sigma L to the reflection sigma 1 that we already know, which has a simple matrix. And we proceed in 3 steps for this. And what we basically do here is we do a coordinate change, where in the new coordinates, the axis L will coincide with the E1 axis. Then we can do our reflection easily, and then we transform the coordinates back into the original coordinate system, so L is back to its old self. And this is a very important principle that you will find very often used in geometry, so pay attention to what we're doing now. The first step, if alpha denotes the angle between L and the E1 axis, so this alpha, then we rotate the whole plane by the angle minus alpha, so meaning we rotate clockwise by the angle alpha. And what this does is it takes L, takes the axis L and rotates it onto the first coordinate axis. So phi index minus alpha applied to L maps L to the first coordinate axis, and all the vectors in the plane also get rotated by minus alpha in the plane. So our vector x that we looked at first is mapped to this vector phi minus alpha applied to x. Okay. In the next step, now that we have rotated our reflection axis onto the first coordinate axis, we can just reflect across the first coordinate axis. So we use the well-known reflection sigma 1 and we apply it to the rotated vectors. So any vector that we want to rotate, that we want to reflect, we first rotate by minus alpha and then we reflect it across the first coordinate axis. So we get the vector sigma 1 applied to phi index minus alpha applied to x. And now in the third step, we rotate everything back into its original position. So we apply the rotation phi alpha to everything. So previously we had rotated L onto the first coordinate axis, phi minus alpha applied to L, and now we rotate it back counterclockwise by alpha. So this axis is rotated back onto the original L. And now the reflected vector phi index minus alpha applied to x, and to this we apply the reflection sigma 1 across the first coordinate axis. We also rotate this by alpha, and then what we get is actually the reflection of the original vector x across the axis L. And this is of course the vector phi alpha applied to sigma 1 applied to phi minus alpha applied to x. And this summarizes it again. We rotate the E1 axis back onto the axis L. So the rotated vector x is rotated back to x, and the reflected vector across the E1 axis is now mapped to the reflection of x across the axis L. So the end result is this linear map sigma L applied to x is given by phi alpha, the rotation by alpha, applied to the reflection across the E1 axis, applied to the rotation by minus alpha, applied to the vector x. And of course this works for any possible vector x. Let me quickly review this. so it's easier to memorize. So this is our initial situation. We have the axis L, which has an angle alpha to the first coordinate axis. And now if we want to reflect any vector x across this axis here, what we do, first we rotate L onto the first coordinate axis, which also rotates every vector in the plane by minus alpha. Then we reflect across the first coordinate axis. And then we rotate back so that the first coordinate axis is rotated back onto L, and this rotates the reflection of the rotated vector to the actual reflection of x across the axis L. And we want to express this in matrices as well. So the matrix SL of this reflection sigma L across this axis L is a product of the matrices that describe these linear maps that we used in the process. So SL is rotation matrix alpha times reflection matrix across the first coordinate axis times rotation matrix minus alpha. Explicitly, I write them out here, and you can multiply it out in any order that you like, and you will end up with this expression here. So this is actually a reflection matrix for the axis that has angle alpha with the first coordinate axis here. It's cosine 2 alpha, sine 2 alpha, sine 2 alpha minus cosine 2 alpha. So note it looks kind of similar to the rotation matrix, but it's not exactly the same. So you see the signs are a bit different. And an important property that both rotations and reflections have in common is that they preserve angles and distances. So they're rigid transformations in that sense. Here I have an immediate comparison of what the two things do. So it's maybe sometimes easier to not just see individual vectors being transformed, but some image. So here I have this house image. And if I reflect it across this axis L, then yeah, you get this. We could describe every point on this house image by a vector from the origin and then compute it for every individual point. And for example, the tip of the house goes here, or this corner here of the roof reflected across L goes here, and the base is reflected to this point. And overall we get this as the reflection. And similarly here we have it for the rotation. Every point in our image here could be described by a vector, and so we rotate every vector individually and we get the rotated image of our original house image. The next class of transformations that we will be looking at are shearings. This one is maybe not so familiar as reflections and rotations are. Now, what is a shearing? A shearing is a transformation, again, I denote it by phi, a transformation with one fixed point axis L through the origin. So that means every point on this axis L is being fixed by the transformation, is not moved. And all other points x in the plane are translated parallelly to this axis L by the shearing. And the distance, how far they are translated, is proportional to the distance of the point to this axis. Now let's look at an example. So if L is the E1 axis, so our first coordinate axis here, then a shearing does the following. So we look at the points on this square here. What happens to those? Each point can be described by coordinates x1, x2. And what the shearing does, if we shear parallel to the E1 axis, every point here gets translated to a certain distance in the direction of the E1 axis. Here we have a proportionality factor A that tells you how far you translate. And also, the further away you are from the E1 axis, the larger the distance that you get translated. So that's why this square here is transformed into this skewed parallelogram. And we can write this in matrix form. So if phi 1 denotes the shearing parallel to the E1 axis, then what happens is we have x1, x2 being mapped to x1 plus a times x2, and x2 is being fixed. And this is a matrix vector multiplication where the matrix, which I call n, in this case is just given by this simple form. So we have 1, 0, a, 1 as our matrix entries. Now, if we want to shear parallel to some other axis rather than the E1 axis, so like we have here, some axis L, which has an angle alpha to the first coordinate axis, then we do this in a similar way that we did for the reflections. So we can use our trick of coordinate transformation. We rotate the axis back onto the first coordinate axis. We do this by doing a rotation by minus alpha, if alpha is the angle here. Then we do the shearing parallel to the first coordinate axis that we just saw on the previous slide. And then we rotate back so that the first coordinate axis is rotated back onto L. So everything is rotated back into its original position. But in between, we perform the shearing, and that will be the shearing parallel to the axis L. And what we get as the matrix for the shearing is then again this product of three matrices. The rotation matrix for minus alpha, which rotates L onto the first coordinate axis. Then the matrix N, which performs the shearing parallel to the first coordinate axis. And then the rotation by alpha, which rotates everything back into the original position. And in this way we obtain the shearing parallel to the axis L. Next, we look at scalings. A scaling, which is also called a dilation sometimes, is a transformation that stretches or shrinks the axis. So it's of this form here. I use a capital lambda to denote this linear map. So lambda of x is simply lambda 1 times first coordinate and lambda 2 times second coordinate, where lambda 1 and lambda 2 are some positive scalars. As an example, let's take lambda to be 1/2. So this coordinate direction gets shrunk by a factor of 1/2. And for the second coordinate, we multiply it by lambda 2 equal to 2. So this one gets stretched. And here I have a little house again to indicate what happens with the points in the plane when we apply this scaling. So along the first coordinate axis, the x1 coordinate, we multiply everything by 1/2. So in this direction here, the house gets narrowed, it gets shrunk. So these sides of our little house become these sides here. And along the x2 coordinate, everything gets stretched by a factor of 2. So we end up with a house that is much slimmer than the original one, but also much higher. And we can represent this scaling lambda by a diagonal matrix A, and it's called diagonal because it only has coefficients that are non-zero on the diagonal entries. So the scaling factors lambda 1 and lambda 2 are on the diagonal, and the off-diagonal entries are 0. And because we can represent a scaling by a matrix, it is immediately clear that it's a linear map. The first remark, as usual, scalings along axes other than the first two coordinate axes can be obtained by composing with rotations, as we've seen for reflections and shearings. And in theory, we could also allow negative scaling factors, but that would just amount to combining a scaling with positive factors and a reflection. So we wouldn't gain any anything new by allowing negative factors. The next type of transformations we look at are projections. So a projection, which I denote by a capital Pi, is a map that takes a vector x or any vector x and projects it onto some axis L. So that means we take the perpendicular line to L, and then parallel to this perpendicular line we drop the shadow of x onto the axis L. That means we get rid of the component of x into the direction of this perpendicular and only keep the component of x that is parallel to our projection line L. And this is the projection of x onto the line L. And again, let's look at the simple special cases that we project on the coordinate axis. So if we project on the first coordinate axis here, what we do is we simply throw away the second coordinate, if you like. So a general vector x has coordinates x1, x2. Projecting it onto the first coordinate axis means just mapping it to the vector x1, 0. And similarly, projecting it onto the second coordinate axis means mapping it to the vector 0, x2. So projections allow us to decompose a vector into its components with respect to the coordinate axes. We can reconstruct x by adding the two projections on the coordinate axis. And we can easily write down the matrices for these projections. So for the projection on the first coordinate axis, we simply have the matrix P1 with entries 1, 0, 0, 0. And for the projection on the second coordinate axis, we have the matrix 0, 0, 0, 1. Now, if we want to project onto an arbitrary axis, we do our usual change of coordinate game. We rotate this axis onto the first coordinate axis, then we take the projection onto the first coordinate axis and then rotate back to the original axis L. So the projection onto an arbitrary axis L is given by the composition of the rotation by minus alpha, the projection onto the first coordinate axis, and the rotation by plus alpha, if alpha is the angle between our axis L and the first coordinate axis. Now I want to look at translations, and as these are nonlinear maps, I will look at a bit more general type of transformations, which are affine transformations. So we choose any vector v and we fix this vector, and then we say a translation by this vector v is the transformation t index v, which if I apply it to a vector x is simply taking the vector v and adding it to the input vector x. And we see the effect here. So if q is this square here, and if we apply the translation tv to q, then every point on this square will be translated by this fixed vector v. So we translate the whole square by the vector v. And as I mentioned before, translations are nonlinear, so let's verify this. If v is not 0 and x, y are any two vectors, then translation by v applied to x plus y is the vector x plus y translated by v. So we just add the vector v to x plus y. This is, of course, if v is non-zero, not the same as taking x plus y plus 2 times v. But this is what we would need to have for linearity. So we can rewrite this if we add one v to x and one v to y as x plus v plus y plus v. And this first one is t index v applied to x, and the second one is t index v applied to y. And if we had linearity, then this one and this one would have to be equal. But as we see here, they are not equal. So translations by non-zero vectors are not linear. Now, what we learned about general geometric transformations so far are how to describe rotations about the origins, reflections across across axis through the origin and shearings parallel to axis through the origin. If we include translations, then we can describe rotations about arbitrary points, reflections across arbitrary axes, and shearings parallel to arbitrary axes. So they do not have to go through the origin of our coordinate system. And I want to illustrate this by means of an example. So I want to realize the rotation psi alpha v, with the center of rotation being a point v with coordinates v1, v2, and the rotation angle alpha. So here we don't rotate about the origin, but some arbitrary point which is described by this vector v here. And again, we will use the principle of transforming this problem to an easy coordinate system and then transforming back to the original one after we've performed the rotation. How do we do that? So again, I use this image of a house to illustrate the effect of the transformation. We know how to rotate about the origin. So if I want to rotate about an arbitrary point v, what I do is I first translate v back into the origin. That means I apply the translation t index minus v. So every point in the plane, especially those on this little house here, is moved by minus v. So the center of this house, which is the point v, is moved to the origin. Next, I apply rotation about the origin by the angle alpha, which is phi alpha. So my original image here has been moved to the origin. Now I rotate it about the origin, so I get this blue house here, which is just a rotated version of the black one, after applying phi alpha, the rotation by angle alpha. Yeah, and then what I do in the next step, I simply move it back to its original position. So I apply the translation t index v. So I take the rotated image and translate it by the vector v, and then I get the rotation with center of rotation at the point v. And this is what I wanted to have. So the affine transformation psi alpha v applied to x, which should rotate any point in the plane with center of rotation v, is first we move the center of rotation to the origin by applying the translation t index minus v, then we rotate about the origin, and then we move the center of rotation back to the original point v. And yeah, I used the term before now, a transformation psi consisting of a linear transformation phi composed with a translation t index v is called an affine transformation. So psi of x, if it's affine, then it is of this particular form here, translation v followed by the linear map phi applied to some vector x, which is nothing else but applying the linear transformation to x and then translating by a vector v. And note, in this definition we allow both the linear part or the translational part v to be trivial. So this could be the identity map or this could be the null vector. So linear transformations and pure translations are special cases of these affine transformations. At last, I want to introduce extended coordinates, which are a convenient way to describe affine transformations. And sometimes they're also called homogeneous coordinates. So we've seen that translations are not linear, and hence they cannot be represented by matrices, because we already learned that matrices and linear maps are in one-to-one correspondence. So if we want to represent anything by a matrix, it would have to be a linear map. Or does it? Well, we can't use 2x2 matrices to represent affine transformations, but in fact we can use a nice trick with 3x3 matrices to represent affine transformations. And for this we introduce the so-called extended coordinates. So if our vector x in the plane has coordinates x1, x2, then we can assign to it a three-dimensional vector, which we call x hat, which contains its 2D coordinates, x1, x2, and for the third coordinate we simply write a 1. And I will also use the somewhat compressed notation that I simply write x over 1, where x denotes the full vector here, so I won't always write out all the coordinates explicitly. And sometimes these extended coordinates are referred to as homogeneous coordinates, which is not completely correct, because homogeneous coordinates mean a coordinate system in projective geometry, which we are not talking about here. And in homogeneous coordinates, they're very similar to extended coordinates, but there you would actually have a whole class of coordinates that are multiples of a vector like this that would all be identified to describe the same point. Now, the translation by the vector v can be expressed in extended coordinates by a matrix, which we then call t hat index v. And it is of this form here, so we just have 1, 0, 0, 1 up here. Then we have in the last column, we have the extended coordinates for the translation vector v, and down here we just have zeros. And the bars in this matrix are just for better readability. They don't have any specific mathematical meaning. Now we verify that this notation makes sense. So we multiply t hat in xv by x hat. So the extended coordinates of vector x multiplied by the extended coordinate representation of the translation. And what we get is this vector here, x1 plus v1, x2 plus v2, and 1. So this is again a vector in extended coordinate notation. And it's precisely the vector x plus v. So what we get if we take the original 2D vector x and add the translation vector v to it and then write it in extended coordinates. So this is precisely t index v applied to x and then put in extended coordinates. If we're given an affine transformation, psi av, where this means that the linear part of psi is given by the linear map phi a, so given by multiplying with the matrix A, and the translational part is t index v, so v is the translation part of this affine transformation. Then we can express this in extended coordinates by writing it like this. So here use a bit of a shorthand notation. We put the 2 by 2 matrix A in the upper left block. Then we have the extended coordinates for the translation vector v, and we fill up with zeros. And this 0 here represents, if we write it explicitly in all the coordinates, it represents these two zeros here. Here we have the 4 coefficients of the 2 by 2 matrix A, and here explicitly the extended coordinates for the translation vector v. And again, we can verify that this is compatible with the extended coordinate representation for the vectors. So here we have x, the vector x, in extended coordinates, and we apply this affine map in this notation to it by using the matrix multiplication. Then what we get is we multiply matrix A up here with x, with the 2D coordinates for x, and we multiply v by this 1 here, so we get ax plus v. And yeah, this is just the vector x plugged into our affine transformation. We multiply it by matrix A, then we apply the translation plus v. And here the 1 remains, because in the second row we multiply vector x by the 0 vector here, so by these two zeros. And the 1 gets multiplied by the 1 here, so we are left with 1 down here. So this is again the extended coordinate representation of a vector, and it's precisely the vector that we get by plugging x into this affine transformation here. So yeah, this works as a matrix representation, 3 by 3 matrix representation for affine transformations. Let's look at a concrete example. So if we have an affine transformation psi represented in extended coordinates by this 3x3 matrix here. So you see here the upper left block, that's a rotation matrix by angle pi/4, so that's a 45-degree rotation. And here the extended coordinates of the translation vector, we have -1, 1. So we translate -1 to the left, or actually +1 to the left because the positive direction is to the right, and 1 upwards. Here this little image shows what we do. So as an example, we look what happens to this vector x on the first coordinate axis. First, we apply the rotation, which is given by this matrix part here. That rotates x to this point. And then we apply the translation given by the part here in the last column. That means the translation by this vector. So we add this vector -1, 1 to the now rotated vector, and we end up at this point here. So this is what happens to this vector x. And maybe it is a bit clearer if we again look at a particular image. So we have our house again. What happens with this affine transformation? We first rotate it by 45 degrees. So we get this green image here. And then we translate it 1 to the left and 1 up. And we get this blue house here, and that is the final image of our original house under the affine transformation psi. So if you like this video, then like it on YouTube, and please subscribe to my channel, because many subscribers will help me produce much more great content for you in the future. And if you don't mind, please watch my videos till the end.